And today we're going to talk about its exact solution by the Jordan-Wigner. Okay, so just a quick recap. So we saw that the Kramers-Wannier duality allows us to convert a sort of strongly coupled problem. Okay, at least if we define, let's say, the coupling to be G, which was H over J. So problem with strong coupling into a weakly coupled problem where we define a dual coupling, which is the inverse of. We found that we could map this to a problem where the coupling is the inverse of the original coupling, and therefore, in terms of that coupling, we are at weak coupling and vice versa, of course. Okay, and so you might ask, well, why does this happen? The reason is that we managed to identify the right degrees of freedom in each limit. In case in physics, we always try to find the good degrees of freedom, which are usually the ones that are weakly coupled in a given phase. And so these dual spins, which physically really were domain wall excitations, well, they are the right, in quotes, degrees of freedom, or sort of weakly coupled degrees of freedom in the ferromagnetic phase. Okay, so in the ferromagnetic phase, the original spins are sort of strongly coupled. They order together, but the domain walls are sort of dilute excitations, and just like the spin flips are weakly coupled in degrees of freedom in the ferromagnetic phase. Okay, so there's one description that, in a sense, is better than the other in a given phase. So that's nice, but it turns out we can do even better than finding the right degrees of freedom in these extreme limits. Okay, we can identify the right degrees of freedom throughout the phase diagram. Okay, in the entire phase diagram. Okay, which is quite remarkable, quite unique. We can't usually do that for strongly correlated systems. And so what's nice is that this identification will include the quantum phase transition, which is what we're interested in. Okay, in the context of CFTs and many-body systems. Okay, because obviously if G is 1, it's neither weak nor strong, and so we need to have a description that includes this intermediate range of couplings where neither the spins nor the dual spins are the right language. So what we'll do is to introduce operators that are the product of the spin, which is sort of original degree of freedom that's weakly coupled in the ferromagnetic phase, and then the dual spin that's weakly coupled in the ferromagnetic phase. And so we'll take the product of a spin and a neighboring dual spin, or domain wall operator. This is one instance of a kind of more general construction in statistical mechanics, where we look at these operators. They're called parafermions in general, and this is one instance of that, which are products of order and disordered fields. So we'll be looking at our little patch of our lattice. Remember that we had lattice sites, direct lattice, which are in white, and then we were looking at these dual lattice midpoints of the original lattice. So for a given site I, there are two neighboring dual lattice sites at I minus a half, I plus a half. And so I'll start by defining a an operator that will be the product of a spin that lives on the site I, and then dual spin that lives on site I minus k. So at this point, we don't really have a good reason to do that. We're just trying something, and we'll see that it turns out to be a good idea. Okay, so I'll define as chi I the product of sigma I z. So that's the spin, and then dual spin z on site I minus a half. So remember that this dual spin mu z was a product of a bunch of sigma x's. It was a domain wall creation operator, and it was flipping all the spins to the left of that dual spin 1 minus a half. So it flips everything up to I minus 1. Okay, so the product over sigma sj. Okay, we're on a finite chain, I'll remind you. So for j from 1 to I minus 1. Okay, so strictly less than 1. And we'll do that for I between 2 and n. And again, just to be very clear, for chi1 will be so I only have site 3/2, and so for chi1 I have a separate definition that that includes just the spin in this case, sigma 1 z. Okay, and so that's one, but I could have chosen also to pair up these guys on the right. So I'll do that as well, and I'll call this tentatively. I'll explain why in a second. I have a question mark here, but I'll call this chi. So by tilde, the same product, sigma iz, but now including the dual spin to the right, mu iz I plus a half. So again, this is a product that involves, it's a non-local operator. It involves the product of all those spin flip operators. Okay, again, to the left of I plus a half. So this time it includes the spin flip operator on site I. Okay, and so I can actually simplify this a bit. So I'll factor out to sort of bring the two definitions in more symmetry, if you will. I'll pull out the sigma x that lives on site I. I'll put it here. And then the product, the string is only over j strictly less than I. Okay, so I have right here. So sigma z, sigma x, this is I sigma y. And then this product. Okay, again, for all I between 2 and n. And likewise, the chi1 tilde I would define as, basically removing this piece here, I sigma 1i. But by convention, I would like to work with Hermitian operators. I'll define the second operator, the tilde with an extra I. So I'll define I tilde actually as minus I sigma iz mu I plus a half z. Okay, so that removes this factor of I here. So it's sigma 1 sigma I y from 1 to I minus 1. Again, for 2, I between 2 and n, and then chi1 tilde is just sigma 1 y. Okay, and so you can check, leave it as an exercise to check that these operators are Hermitian. It's not that hard. Okay, so these two factors commute, and they are Hermitian. Okay, and so one more thing we can say about these operators, they're square root to 1, they're products of Pauli matrices. So it's not hard to check that chi1 squared, chi I squared, and chi I tilde squared is squared to the identity operator, and slightly more involved, but again, not very hard. That as an exercise is to show that these chi's are very interesting because they're actually fermions. Okay, so they obey, they're defined in terms of spins, but they turn out to be anti-commuting variables, and they obey, the Clifford algebra, so the standard anti-commutation relations of Majorana fermions. So the chi's and the chi tildes form independent sets of real fermions. Okay, so the chi and chi tilde anti-commute with each other on all sites, and then on a single site, they are properly normalized to be Majorana fermions. Okay, so the surprise, if you will, is that these operators are Majorana fermions. So this is the mapping, if you will, of spins to fermions is called the Jordan-Wigner transformation. Very useful tool to attack problems in 1D quantum magnetism. We can map problems of spins to fermions. And again, the basic idea is, we're attaching a particle to a defect, right? So we're attaching a spin flip to the domain wall. And so, in a sense, there's some statistical transmutation happening from this binding of a string operator and a bosonic spin. So that's nice, but how does it help us? Well, we want to see what our transverse field Ising model looks like in terms of these fermions, these Majorana fermions. Okay, so if these are Hamiltonian, will have a simple form in terms of these fermions, otherwise it wouldn't be very helpful. So I'll do it sort of in reverse. And so I'll consider products of Majorana fermions and see what I get in terms of these spins. Okay, so if I take chi tilde I chi I, have sigma I y, then this string of sigma x's, I have sigma I z. For the chi I, the same string. Since there's no I appearing in those products, then I can commute those things past the sigma z and the sigma y. And so these two strings cancel out. So I have sigma I y, sigma I z, which is I sigma I x. And therefore, sigma I x can be written as a bilinear of Majorana fermions on the same site. So that's going to be our transverse field term. It's nice. It's a simple bilinear in terms of fermions. And I can also look at the product of Majorana fermions on different sites, also different flavors. And what I get is sigma z I plus 1. So this is now I plus 1. And so now this is less than I plus 1. Sigma j x, sigma I y, product 1 in j and I, and 1 in I. And so to cancel out the strings, I'll just pull out one factor here. Okay, so I have sigma I plus 1 z, pull out the sigma I term. Then the product is for j strictly less than I, sigma I y. Again, the same string here. This string cancels out. There's no I term in the product. I have sigma I plus 1 z, sigma I x, sigma I y. So I have I, sigma I plus 1 z, sigma I. Okay, so that's very nice because I have this energy density, this bond energy of the Ising model. And so again, very nicely, this can be written as a bilinear of Majorana fermions. Okay, so that is chi I plus 1, chi I tilde, or chi I tilde chi I plus 1. Okay, so that's very helpful because you can write down my transverse-field Ising model in this form minus ij. So the exchange term is this one, I1 to n minus 1, I tilde I plus 1 plus IH, the transverse field term, 1 to n with these fermions paired on the same site. Okay, so we started from some strongly interacting spin Hamiltonian, and we end up with remarkably a free fermion Hamiltonian. Okay, so that's very nice because now we can diagonalize for any G, any coupling. Okay, and so this is also, these fermions are also in disguise the essence of, the Onsager solution in the classical language, but it's much easier to see that they're fermions when we work with the quantum problem. Okay, so if we want to work with to the more standard many body language, then it's nice to combine these objects into ordinary sort of complex fermions. So we can combine them into a single spinless complex fermion. Okay, and we would like to do that because we'd like to have a well-defined Fock space and so on with a number operator, occupation numbers. So if I define Cj to be 1/2 chi j minus I chi j tilde, a dagger. Okay, remember that these chi's are Hermitian. Okay, or in other words, chi j, you can think of it as the real part of this spinless fermions, the spinless fermion chi j tilde as the imaginary part. Then obviously we can show that these operators obey the usual commutation relations for fermions. Okay, so we'll work with these and our Hamiltonian in terms of these complex fermions and see what we get. So we get j1 to n minus 1, Cj minus Cj dagger, Cj plus 1 plus Cj plus 1 dagger plus H j1 to n 2 Cj dagger Cj minus 1. If I expand this out, get minus j minus 1 Cj dagger Cj plus 1 minus Cj plus 1 plus H C. Okay, and then j1 to n. Okay, so what's this? Well, it's simple enough. So this is just a free fermion hopping term. There's some chemical potential, and now there is a nearest neighbor pairing term. So this is a sort of BCS, a one-dimensional P-wave superconductor. So the model doesn't have, we have fermions, but we don't have conservation of the fermion number. So you can go back and see what this particle number conservation symmetry would mean. It would correspond to a conservation of the total spin at Z. So if we had a model, for example, like an XX spin chain, we would just find this free fermion hopping without pairing term, but our Ising chain does not have a Z conservation. Therefore, we get pairing terms. So, so it's quite nice. There's a mapping from, again, this spin chain problem to a mean field superconductor, and we can try to understand its physics. Okay, again, recall that what we're trying to get at are the critical properties of the Ising chain, and so we'll focus on the physics of the quantum phase transition, which we know from Kramers-Wannier duality occurs at G equals 1. Okay, and so here, up to here, I've been careful, to keep all the terms for the finite chain with open boundary conditions. At this point, I'll be a little bit less rigorous. We'll focus on the thermodynamic limit we're interested in sort of bulk thermodynamic properties, even though after we've talked about the critical point itself, I'll go back to looking at the finite chain because boundary effects, again, will be important to account for, all the proper ground state degeneracies and so on. But for now, let's ignore boundary effects because I want to work in momentum space to diagonalize this this free Fermionic Hamiltonian. So we'll invoke periodic boundary conditions and work in K space. Okay, again, feel free to interrupt with any questions. Okay, so simple enough. So we just introduce a Fourier transform, e to the I kj, Cj. So we go to momentum, Ck here, momentum space. So if you do this, okay, so the this hopping term, of course, gives us the usual cosine dispersion. And this term is the usual chemical potential term. So we get 2, so the chemical potential, I'll put it here, which is H, then J, which is the sort of effective hopping strength, cosine K, Ck, dagger Ck. As usual, I'll call this single particle energy measured with respect to the chemical potential Ck. And then we have a pairing term. So it's not an on-site pairing term. So there is some K dependence in the gap function. It's an odd parity pairing. So we get J, Ik, Ck, C minus K, Ck plus Hermitian conjugate. Okay. And then again, because I do care about ground state energies, there is a constant piece that I'll keep here. All right, so this is our free Fermionic Hamiltonian. So again, we have off diagonal terms in particle hole space. And so to diagonalize this, we'll introduce an Nambu spinner. Okay, so we'll double the degrees of freedom by defining an Nambu spinner. Capital psi of K, which is a 2-component spinner, Ck, C minus K dagger. The dagger is a row spinner, Ck dagger, C minus K. In terms of this object, we can write our Hamiltonian. Since I've doubled these degrees of freedom, there's a 1/2 here, and I have sum over K, psi K dagger. And with a matrix, so on the diagonal, I have the energies Ckn minus Ck, and then I have pairing function delta K. It's annoying, but okay. Minus this constant piece. And again, just to be careful here, there's a 1/2. When I do this particle hole description, there is a 1/2 Ck. Okay, but this actually nicely cancels out because this is, 1/2 sum over K. And inside of Ck, there's a 2H here, and then minus 2J cosine K. This is just NH, which cancels out against minus NH. And this is a sum over a periodic function with 0 mean. So I get 0.
We have a question.
Yep.
So initially, I think you have an open channel, and then
yes,
close it, and so the top equation requires a C1 equals Cn, right?
That's right. Yeah. So here, as I was saying, I'm being a little bit more, cavalier with that. So I'm just naively diagonalizing the free fermion problem with periodic boundary conditions. You might object to say, okay, I won't capture the right boundary effects and so on. But once we've done this analysis, I'll go back to understanding this fermionic chain with open boundary conditions.
So I think that Hamiltonian itself is default degenerate.
The Hamiltonian itself.
1D P waves, for example.
Yeah, that's right. So we'll have, these Majorana dangling modes.
Yeah, but now you close it.
That's right. So here I'm interested, I'm doing this because I want to look at the physics near the transition, where the system becomes gapless anyway. And so I'm not interested in boundary effects to answer that question. And then to understand, at the end, I'll just, as we did, can we understand the two phases as we did with Kramers-Wannier, now from the point of view of the fermion problem. And there you certainly need to keep these boundary modes, because again, you will account for the correct degeneracy in deep in the phase. But the point here is just that when you're interested in the critical physics, at the transition point, then those boundary effects do not affect the critical exponents, for example, which is what I'm interested in capturing. Yeah. Does that make sense?
No, I just don't really know why boundary effect do not affect physics at the critical point. Yeah, so at the critical point, right? So this degeneracy will be important when we're in a gap phase, right? So in the ferromagnetic phase, there's a twofold degeneracy. The paramagnetic phase of ground state is unique, but at criticality, that's not really what there's no broken symmetry. You're in between the two phases. So what you're interested in is knowing, for example, how this excitation gap closes, how that scales with distance to the critical point. And so this bulk, you're interested in the bulk thermodynamics, and the boundary does not affect that.
But
yeah, maybe I'm wrong.
Even in the gap phase, if you're looking at correlation functions of local operators,
right,
in the bulk, the boundary effects shouldn't matter either, right?
That's the intuition here, right?
It's especially true in the paramagnet.
Yes. So no, that's right. I mean,
not only the critical point. If you're considering local physics,
sure, right.
In the bulk, it's a local model, right? Local model. So the boundary is like 10 light years away, then.
Yeah, I think the only point that we'll get to as well, which is the fact that the twofold degeneracy in the ferromagnetic phase, right? Which we think of as it's a bulk property. Well, in this free fermion problem, you have these dangling Majorana modes that capture this physics. So there's the spontaneous symmetry breaking in the spin language is described in terms of sort of topological degeneracy, if you want, in the fermion problem. So if you want to ascribe that to boundary modes on an open chain, you can do that. But yeah, in principle, you could also still see it in a periodic system with these fluxes.
So when one talks about phase transition, we only think of bulk properties.
Well, you can ask whether there's some boundary effects as well. Sure, that's another question. But here we're interested in bulk critical properties. So I guess I would say right. So correlation functions of operators in an infinite system or in the bulk. You could ask whether on the boundary there's different exponents. That's something that can happen for sure. Sort of boundary criticality and so on. But we're trying to answer sort of simpler questions, you could say. Yeah.
Basically, for your bulk quantum criticality, you look at the free energy density.
Right.
That's the whole point. The free energy density. So that you forget about. So there are no boundary effects in the free energy density.
Right. They would be subleading. You divide by n. Right.
So you divide by n. That's the key quantity you look at when you look at bulk criticality.
Right.
And surface criticality is a different topic, right? But for bulk criticality,
right.
Intensity.
That's right. Yeah, that's certainly how I think about it. Yeah. That's right. That's how I think about it.
I'm missing.
I don't think so. No. Again, I think there is no spontaneous symmetry breaking in the critical phase. It's like saying if you have a topological insulator or a superconductor, but now you're not. You might say boundary effects are important, but once you tune at the transition between a trivial insulator and a topological insulator, what matters is there's a gapless Dirac cone in the bulk, for example. And that's what dominates all the physical properties that are, intensive in the sense, or all the densities, which is what you care about, right? We care about singularities in the free energy density or the ground state energy density. Yeah, thanks for the question. Okay, good. So there's only a few more steps really to get to those critical properties. So we've written down our Nambu problem. It's just still need to define what this delta of K is. This is from this nearest neighbor on parity pairing. So delta of K is 2 ji sine of K. So again, pairing function is odd in K. And so the Hamiltonian is, okay, so I diagonalize this matrix. I get these Bogoliubov excitations with energy capital E of K. Okay, so I have these two flavors of Bogoliubov excitations. Okay, they're related, negative energy and negative frequency, positive frequency, or this quasi-particle energy is root Ck plus modulus of delta K squared. Okay, so writing it out, we get 2j square root 1 plus g squared minus 2g cosine of K, and g is h over j. Okay, and from this, for example, we could compute the free energy, the ground state energy density. There'll be some integral over K in the first Brillouin zone, and that's very nice because if you look at on Sagard's solution, there's some integral over some parameter theta from 0 to 2 pi, and it's it's a bit hard to understand where this comes from, but it's really just the quasi-particle contribution to the free energy, right, of these occupied Bogoliubov quasi-particles. So it's very transparent in this 1D problem. So again, what we care about, okay, so that's an exact solution of the problem, complete solution. Again, we're interested in critical properties. So the claim is that something special happens at g equals 1. So what happens? Well, if you look at this spectrum, I'll draw it in a second, but this Bogoliubov spectrum is fully gapped g different than 1 and becomes gapless for g equals 1. Okay, so as we should hope, because there should be some singularity in the ground state energy of this this free, not interacting, but many body problem. So qualitatively, this excitation spectrum looks as follows: as a function of K in the first Brillouin zone, pi pi. Okay, so for G different than 1, the spectrum sort of looks like this. Okay, this would be G either less than 1 or greater than 1. It's fully gapped. But at G equals 1, then at K equals 0. Okay, so if K is 0 and G is 1, and we have 1 plus 1 minus 2, the spectrum becomes gapless. Okay, so it's a kind of Lifshitz transition, if you will, just gap closing transition in the free Fermionic language. It's like a gap closes at exactly at G equals 1 and at K equals 0. So to read off the gap, we just need to look at what this is at K equals 0, and you just get so now delta denotes the the many body gap, if you will. It's 2j modulus of 1 minus g. Okay, so right, so in general, in quantum criticality, we expect that, as I briefly alluded to at the beginning, there is an energy scale, often a gap that closes at the critical point. Okay, so here's a very simple linear function, close at GC equals 1. Very good. Okay, so that's very nice. It tells us what is the continuum critical theory, because if we linearize this lattice dispersion relation near K equals 0, we get a continuum theory. And so we've isolated the continuum, CFT, if you will, theory of free massless Majorana fermions in 1 plus 1D. More generally, there's some Ising CFT with permanent fields and so on, but for us, we can just focus on this this simple picture. And so already we can read off some critical exponents. Bring this one up. From this exact solution. So the excitation spectrum, first of all, is linear in momentum at criticality. Okay, so remember my plot that's below here, the spectrum crosses linearly. And so E of k at g equals 1 is on the lattice, it's 4j absolute value of sine k over 2. If you linearize near the gap closing point, it's linear. So C modulus k, where C is 2j. So there is a speed of light, if you will. There's a velocity and there's a linear spectrum. And so from this, we read off that there is a dynamical critical exponent z equals 1 for this transition. Okay, so it's already interesting. There's we start from some lattice system, but there's an emergent Lorentz invariance at criticality, which is often a recurring theme, which is why we can talk about conformal field theories, even though we start from lattice systems that have no conformal invariance. Yes, just 1 second. Add the QPT. Yes, question. Yeah.
Just for the sake of clarity,
yeah.
Just define what is the diameter.
Oh, very good. Yeah, that's right. So I'm just going to write this. So, so it's essentially, if you have a dispersion relation for the excitation that goes like, omega will go like k to some power in general, and that power, that's what we call z. It also shows up in the this many body gap. So generically, near a continuous quantum phase transition, it will go like this gap will go like z nu, where z, it's a really kind of a dynamical part of the spectrum. Shows up here, as well as this correlation length exponent nu, which given z being 1, we can read off that it is also 1. Okay, in other words, if you want the energy scale, goes like an inverse length to the z power. The inverse length for the gap is the inverse correlation length, which itself goes like g minus gc to the nu. We put these two things together. And here we read off that nu is 1, which is the correlation length exponent. Is generally you would say, So that's already interesting because this nu is very different from a sort of Landau theory, pre-Gaussian nu, which would be 1/2. Okay, so it's a non-Gaussian critical exponent, even though from the exact solution, it's just a kind of trivial consequence of having a gap closing transition for pre-fermions. Okay, so just a few more things, and then we'll stop. So this is where this question of boundary modes will come back, because just to sort of wrap up the discussion. So we're getting some critical properties. To get the other exponents, one has to work a bit more. For example, the eta exponent. So I won't get into that in these lectures, but one could do that. Here, I just want to again revisit what the phases are in the fermion language. Okay, so we looked at them in the original spin language, in the dual spin language, and finally, what do they become in the fermion interpretation? So again, we'll look at the limits where this is simplest. So the paramagnetic phase. Okay, so they're all sort of superconducting phases in one dimension, mean field superconducting phases. So if G, okay, the paramagnetic phase G is much bigger than 1. So our dispersion, remind you, was 1 plus G squared minus 2G cosine K. If G is much bigger than 1, then essentially this constant piece takes over. So we get a dispersion that is 2G 2J times G, which is basically 2H. Okay, and so the spectrum is flat, so we get our PIFM Hamiltonian, which is in the Bogoliubov form, the diagonalized form, gamma k plus minus gamma k minus dagger gamma k minus. Okay, so it's a gap superconductor. It's a gap superconductor, and so I think about the picture of the ground state. Again, I have my E of k here. Okay, I have my Bernoulli zone, pi minus pi. The spectrum is completely flat, and it's a superconductor. I just occupy the negative energy modes. Okay, so I just occupy all these states. Okay, and the excitations are just quasi-particle excitations. You can think of these as particle hole excitations. You know, so here there's a particle that is fermion that is promoted from here to there, and that's the lowest energy excitation. Okay, so it's a gapped superconductor, and the lowest energy excitation is a BDG quasi-particle. Okay, so here, here this then here is at minus h. This one is at h, and so the energy is 2h. And this limit that agrees with what we understand from the spin language. So again, you know, remember that in this Bogoliubov formalism, you know, these are not actually independent excitations. The total number of these plus and minus Bogoliubov quasi-particles is fixed to be n, and so we can only have these the quasi-particle excitations. So again, this is consistent with energy cost of a single spin flip. Okay, so we're in a paramagnetic phase, you know, deep in the paramagnetic phase. Okay, so because remember that the ground state was paramagnetic phase. The ground state was a bunch of spins, you know, all in the x direction, and then we flip this orange guy like this. Okay, so here we had a Zeeman energy of this spin, you know, minus h, and here there's a plus h, so the energy cost is 2h. Okay, so that's clear. In K-space, now, just to be sure that we're not missing some physics by going to K-space to address maybe your concerns. So if I went back to the original real space Hamiltonian for the fermions in this limit, so in the Majorana fermion, working with these Bogoliubov quasi-particles, then the Hamiltonian in this limit was what? It was the h term dominated, so we get IH sum 1 to n chi I tilde chi I. Okay, so then let's stick with this Majorana picture. What this tells us is that on every site we have chi and chi tilde Majoranas. Okay, so I have a bit of a kind of a ladder of Majorana fermions. And so what happens in this limit is that, you know, these Majoranas, if you will, become paired like this on every site. Okay, so that's the picture. Simple enough. And it's very clear that there's a unique ground state here, right? So, you know, these chi I and chi I tilde are paired on every site. Okay. Now, let's turn to the ferromagnetic phase. With this board. Okay, so if in the ferromagnetic phase, okay, so again, this is G much less than 1. The spectrum was 2J square root 1 plus G squared minus 2GK. If G is basically 0, then EK is approximately 2J. Okay, so H is replaced by J. Again, we have a picture of a gap superconductor with 2 bands minus JJ. Again, we occupy all this negative energy states. The gap superconductor, again, we have the lowest energy excitation is again a particle hole excitation. Okay, so this is a BDG quasi-particle with energy 2J. And this is essentially, domain energy cost to create a domain wall deep in the ferromagnetic phase. Deep in the ferromagnetic phase. Okay. So again, we could just look at this, right? We'd have, for example, a state like this where we have, a bunch of ferromagnetic oriented spins. If I look at one bond, I had an energy gain of minus J. If I flip, if I create a domain wall, now this energy cost is plus J. So this costs me total 2J. Okay. So that's fine. The final comment is just to understand where the ground state degeneracy comes from in the ferromagnetic phase. Full degeneracy. So again, we are going to our real space hopping description. Okay, so you probably can guess what happens. So to admire on a picture, our Hamiltonian now is the exchange term that dominates. So in this Jordan-Wigner representation, we had I. Okay, so now again, I'm working with the exact mapping where I have n minus one of these terms, and I have some bilinear involving I and I plus one for the chi and chi tilde. So again, if I draw this pictorially, the chi is here, the chi tilde is here, and I recite 1, 2, and so on. With n, so now, right, so for, let's say the first term, it's chi tilde 1 with chi 2, chi tilde 1 with chi 2. So I'm going to pair these Majorana fermions in this way. And now, because I have a boundary, then you see that no matter how long this chain is, I will always have these two unpaired Majorana modes. Okay, and these ones are chi 1 and chi n tilde. Okay, and you see that these are absent from the Hamiltonian, which is what we mean by unpaired, and therefore these operators commute with the Hamiltonian, and so they are zero modes. And therefore, if I write down my ground state wave function, then I will write down some BCS wave function for this condensate involving all these paired Majorana fermions, but actually there's two degenerate wave functions. This, let's say one of them, the BCS wave function, and an F dagger acting on the BCS ground state. These two are degenerate, where F is a complex fermion that I construct from these two unpaired modes. Okay, chi 1 plus I chi n tilde. So again, this fermion operator commutes with the Hamiltonian. It has its own two-dimensional Hilbert space. Okay, and so this Hilbert space, this zero energy level can be occupied or empty at no cost in energy. So, okay, so quite nicely in this Jordan-Wigner representation, the degeneracy we get from spontaneous symmetry breaking in a spin language, and to some extent in the dual spin language, under the Jordan-Wigner transformation, it becomes a topological degeneracy. There's different ways in which we can understand this, but there's the usual picture of this degeneracy being protected from local perturbations and so on, due to the fact that these Majorana modes are spatially distant, and that's the fermion picture. Okay, so basically done. So are there any questions? Today lecture, yes.
I'm forgetting now, but if we do this on the non-finite system, we get an F dagger.
If you do this, well, okay, so here, so this is in this extreme limit, right? So I've taken J to be much bigger than H. And so these Majorana modes are strictly localized when you consider finite, H, then yes, then these zero modes will have some exponential tail, right? Because there's the H term has this chi I tilde chi I, right? So then there's some mixing, and that's right. So it becomes the correlation length essentially in the Ising model. It becomes finite in this so it becomes essentially 0 in this extreme limit, and then it's non-zero as you move away from this infinite J coupling. That's right. Yes. So this is where you need the thermodynamic limit to get this exact degeneracy.
And what happens if you act with F on the DCS process instead of F diagram? Are they not linearly independent?
If you're saying if you act with, well, let's say this is the one. I define this to be the one where this zero energy mode. So your spectrum will have some states then that will have a zero energy level here, and I'm either leaving it empty or occupying it. I suppose it's a matter of definition. Yeah, but so there's some fermion number parity essentially that distinguishes these two ground states. Yeah, I mean if you act with F dagger on this, this annihilates this state. If you act with F on this, suppose it annihilates this state as well. Yes, questions?
So for the spontaneous symmetry breaking, the degeneracy from that, it seems that so when you add a little bit of perturbation, you break the symmetry. But when you look at the topological degeneracy, it seems more robust against say local perturbation.
Yeah, well, I mean, right. So as we were saying, so there is this there's a finite splitting that occurs if the system is finite, right? Because, and again, if you're at infinite coupling here, then it doesn't matter if the system is finite. But for any if you're not in this infinite limit coupling, then the finite size effect will give you a splitting, which is consistent with the fact that very small, exponentially small in the system size. But that's consistent with the fact that to see true spontaneous symmetric breaking, you need to be in the thermodynamic limit, or in the limit where you have the symmetric breaking field, and then you take the thermodynamic limit. Otherwise, you don't have an exact degeneracy. Which is just this usual idea that you can always go from all the up spins to the down spins by performing tunneling events, but you need to flip n spins. So that's an exponentially small probability to do that. So that's your sort of small splitting between the two ground states. So you recover this exponential splitting, which is the standard sort of tunneling picture, macroscopic tunneling picture, from a overlap between topological boundary modes, which is an interesting sort of different perspective on the SSB that works in this case.
So if I add a Zeeman term, what kind of operator would I get?
Oh, you mean, I see. If you add like a symmetric breaking field, like a longitudinal field.
Yeah.
Right. Well, in that case, so if you were to add a sigma z term, I see. So if you added some like HZ, right, something like this.
Yeah.
You're asking what happens in the fermion language.
Yeah. Yes, I guess sigma z. What's this operator in the fermion?
Yeah.
It's a primary field in the CFP.
Yeah, in terms of the fermions, it's not a simple operator in terms of the fermions.
I think the duality holds. You get like either you get something that violates from it's just a single Majorana operator or a string.
There's a string. That's correct. Yeah. So the string does not cancel if you try to write down this operator. So it's a non-local thing. That's right, because it's like this is really trying to write the scalar field in terms of a fermion. So there's going to be a string in this case. Yeah. So with a longitudinal field, you cannot. The model is not exactly solvable anymore. And there's lots of interesting physics, right? If you perturb this critical point with a longitudinal field, you get this very interesting spectrum of this sort of E8 physics and so on. So it's quite different, right? But from the point of view of symmetric breaking is the usual thing, right? Where you need to take this order of limit matters.
So what symmetry protects this topological degeneracy?
So I don't think there's any symmetry here. The only symmetry the model has is fermion number parity, and which is a symmetry of any fermionic Hamiltonian. So it's not a, it's the usual thing where, if it's a free fermion topological phase, do you talk about, intrinsic topological order or, SPT like? I mean, Fiona mentioned this thing, right? Different people think about it in different ways. I think there's no symmetry really that protects this model. You can think of it as a model that is protected by a fermion number parity, if you will. I mean, I don't know what's the modern perspective on it. Yeah. Okay.
I think that's the
Right. But in any fermionic Hamiltonian preserves that symmetry. You cannot write down a Hamiltonian that has, a single fermion or a 3 fermion term. It's a Grassmann number. It's not a valid Hamiltonian. So I would say that it's a symmetry, but it's always there.
and low energy, that symmetry might break.
I don't think it's physical. You cannot break that symmetry. It would mean that you can spontaneously create fermions out of the vacuum, which is not a physical thing. No, that's right. So
you could gauge it to get a model where the fermions should be viewed as emergent. But
right.
Fermion parity is the fundamental. If your microscopic particle,
You can gauge it, but you cannot break it, right? Yeah, that's right. You can remove the fermion from the spectrum, but you cannot have fermions being spontaneously created out of the vacuum, right? Which is what breaking the symmetry would mean.
And to be clear, if you gauge the fermion parity, quotes, because it's a little mistake of the notion, but you can think of that as passing to a model where the microscopic degrees of freedom are bosons and the fermions are emergent, fluxes.
Right, and you can only create pairs of fermions, I presume, right? You cannot have like a single gauge invariant fermion degree of freedom. Right.
But there is some relationship.
So in this case, would you say that these fermions are emergent in that sense, presumably?
In the type chain, I think you Hilbert space microscopic.
Right.
Fermions.
But in the Ising chain, in a sense, the
well, in the Ising chain, they're not local, right?
Right.
If you are looking at building fermions from Ising spins, yes, they are emergent, but there's some kind of complicated,
states, excitation.
domains.
Right.
I was just trying to say, but when it's that turn, it breaks not a lot to both duality.
So you're worried that the
There's actually
this term?
Yeah.
Yes, that's a term that breaks. No, but this doesn't break fermion parity. This just breaks the global Z2 symmetry of the model.
Yeah, so I think that's B2.
The Z2 symmetry.
I think that's mapped to the Z2 fermion parity.
But there's a difference between having the fermion parity and having the degeneracy, right? So there's a fermion parity given and fermion parity on state, right? And the statement, the conservation is that those two are different sectors of the Hamiltonian that can't be mixed, right? The symmetry doesn't actually require them to be degenerate.
Okay, then it cannot. Then I think this degeneracy is not logical. When one says logical, it says.
Well, for one, if you have an open chain or a periodic chain, then
boundary condition. So it essentially cut the wire. So this is a significant thing.
Right, but if we stick with the free fermion Hamiltonian, there is a degeneracy for the open chain, but not for the closed chain.
Yeah.
For the free fermion Hamiltonian. For the Ising chain, as we said, it's a bit more difficult. Yeah, because then you need to look at sort of different boundary conditions on the fermions. So there's kind of two free fermion Hamiltonians you need to write down. But because, of course, we want to see SSB regardless of the topology of the chain, because you're right, of course, in the Ising model, it's a conventional symmetry breaking phase. But if we just write down this free fermion Hamiltonian that I wrote down earlier, then yes, then the ground state degeneracy depends on the topology of the chain. So maybe that's where you're getting at.
Versus the bottom. I mean, the bottom still has a fermion parity symmetry, but it doesn't have.
Right, that's right. But correct. But if we had periodic boundary conditions, then of course we would get a unique ground state for both, right? Because there would be no dangling modes here.
So if I can tune the edge, say from very small to very large.
This one?
No, not this.
No, the original, the transverse field. Yeah.
So then I can tune to
G, yeah, the coupling constant.
Right.
Yeah, J, yeah,
So I can run from very small and very large.
right.
So that means I can continuously go across.
No, but the bulk gap closes, right? There's a gap closing transition. The spectrum, is flat, and then it becomes like this, and it becomes like this, and then there's a crossing, right? And then so then these wave functions, these boundary modes, they have a wave function that decays exponentially, then more and more until it kind of merges into the bulk. So there's no continuous. There's a phase transition in between, right? That's just the usual sort of gap closing transition between a topological and a trivial insulator. Or does that make sense? Maybe we can discuss offline potentially. Any other questions?
How about the other critical exponents?
Yeah. So my understanding is that, for example, right, you might want to compute the eta, right? That's right, delta sigma, right? The dimension, right? Something like this, right?
The missing one of those.
Yeah, that's right. So
Parameter.
the order parameter, that's correct. Yeah. So for this one, so my understanding is that computing it directly is difficult. So what people often do is they consider a theory that has basically two copies of this model.
But directly you're using the fermionic solution.
Yeah. So if you just work with the Majorana fermions, yeah, I've never done it myself, but the claim is that it's messy. So what people do is you consider two copies of this model, and then you combine these two Majoranas into, pairs of Majoranas into Dirac fermions, and then you compute the square of the correlation function. That's easy to compute in bosonization, and then you take the square root, and you get the right exponent. So this is, for example, discussed in Shankar's book on field theory and kinetic matter. Yeah, that's it. And the rest, as you said, we can get using these hyperscaling relations. Yeah. So for the yeah. So my understanding is that to get the what it's 1/4, I forgot what it is. The eta. Yeah.
On the dimension.
Right. That's right.
It's called alpha sigma dimension.
The full dimension. That's right. Yeah, that's right. That's right. So in the Jordan-Wigner picture, that the claim is that's the simplest way to get it. You can do the square, take the square root, and then you get it.
What's the answer? Is alpha sigma is 1?
Well, you need to. Well, usually, what is it? Right? It's d plus something like this. I guess. I don't know. I often get these things wrong. But just not. Eta is 1/4.
Because the scalar has the dimension 0. 1+1.
Yeah. Oh, maybe
But
it's.
this has dimension, I think 1/4.
Maybe this is wrong. It's d minus 2 over 2 plus eta. Probably. So 2 minus 2 is 0, and then you have the eta, something like that. Yeah, I think it's 1/8. It's 1/8, right? I never know.
So we just put names on things. So the fermionic chain, you get. So is this what people call a Guitav chain?
Well, it's a special point in the Guitav chain in a sense, because you have J and then the delta, right? But here delta, the pairing strength is also the hopping strength, right? But it doesn't have to be that. So in general, in the context of topological superconductors, people have a hopping strength and a pairing delta and a chemical potential. So in the Ising chain, you have T equals delta, but it doesn't have to be that. So the phase diagram of the Guitav chain is a little bit more. Of course, there's no new phases, but yeah, it's a little bit of a bigger phase diagram.
Including this chain.
Including, correct. Yeah, special point there. Yeah, and then you have the strong pairing phase, which is the trivial phase when basically mu is sort of outside the band, and then you have the weak pairing phase, which is when the chemical potential is in the band, and that's where you get this non-trivial physics. Yeah, so small h.
My co-organizer asked me questions.
Yeah. I can't do anything. I have to keep answering.
Okay, so say I want to solve this in the field theory picture using the Landau-Ginzburg.
Right.
5-4 field theory.
Yes, which I'll talk about in the next set of lectures.
So I've never done this in 1+1.
Yes.
For the 5-4 field theory. Then you do like
You can extract.
expansion, like a 2 plus epsilon and get reasonable
You-
things or.
Well, you can extrapolate the exponents for the form minus epsilon. You can't do 2 plus epsilon because epsilon is 0. But you can do form minus epsilon, extrapolate epsilon equals 2. Whether I think you get results that are not terrible, actually, but I'm not entirely sure. You can resound to extremely high orders. I think you have up to 6 loop or maybe 7 loop for Ising for phi4. I'm not exactly sure how good the exponents are. Obviously, we don't need them because we have the exact exponents. But I think it was not terrible, actually.
Like large and.
Yeah, that's right. Extrapolate n to 1. Yeah, I think you get large n. It's hard to go as high to high orders, right? So I think you have exponents to maybe 1 over n cubed, maybe more. I'm not sure. But yeah, I don't know for sure how good these are in large n. I think epsilon was not as bad as one might guess. Yeah, and n equals 3. It's very good. Yeah, it's quite good. Yeah. With these pedes and so on. Okay.
Such a fixed point exists between 2 and 4.
Yes.
Including 2.
Well, it's
Speaking, or
yes, but still, Mermin-Wagner's allows it, obviously. So, right. So it's the yes, the lower critical dimension is still not the lower critical dimension as opposed to 2 and higher, n equals 2 and higher. So it's still there. So that's why it's still meaningful to extrapolate in a sense. Yeah, I mean, obviously it's still there because epsilon is just some variable. But yeah, that's right. But if you work directly with the Landau-Ginzburg theory in 2 dimensions, then that's not a very good approach because then it's the perturbation. There's infinite number of marginal perturbations, right? So it's not very helpful. But in form minus epsilon, yes, you can do some. Okay, so I guess there's a question there. Yeah.
What? The only in a transverse-field model is with itself.
Kramers-Wannier?
Yeah. In that case, it was the duality between IR and. I mean,
No, it's a duality between sort of weak coupling and strong coupling at all scales in a sense, because it's an exact lattice duality. But yeah.
I was trying to say. So that wasn't exact.
That's right. So it's stronger than these field theoretic dualities because it's not just a duality between infrared fixed points, right? It's a duality between the lattice scale, exact duality all the way from UV to infrared, which is why it's very powerful. But these are quite rare. The Jordan-Wigner?
Yeah.
Yes, it's an exact mapping. So yeah, so it's amazing. It's beautiful. So I mean, in a sense, you might say, oh, this transverse-field Ising model, actually it's a pre-fermion model in disguise, and maybe it's not so interesting. But if you think about it from from the original standpoint, it's a strongly correlated spin model. So it's very non-trivial that you get this mapping and you get very non-trivial exponents. So, and again, the correlation functions as we're discussing in terms of the fermions, yeah, it's not trivial. It's a complicated beast because the fermion is a non-local thing, or sigma is a non-local object in terms of fermions. But yeah, it's very rare. I'm not aware of many other such exact dualities. Yeah, usually in higher dimensions, to my knowledge, they are IR dualities, right? I mean, we have, for example, duality between the Ising model in 2+1 dimensions and an Ising gauge theory, but it's not a self-duality, so it doesn't help you to solve the problem. So that's quite unique. Yeah.
Are we using the full capacity of this? Can we add more terms, more complex terms to the transverse axis?
Well, I mean, you can certainly add things like you can add maybe longer range hoppings, although then maybe you get interaction terms, right? Because you have a string there, and then the string involves fermions. So there's not a ton of wiggle room. So other perturbations. I mean, right? I mean, yeah. There's other models, like I said, the X spin chain, right? Which is SX plus SY. That's also exactly solvable. It's just the hopping term. So it's just a cosine K dispersion. It's another exactly solvable model. There might be others, but yeah, I think they're all quite well known. I don't think there's anything non-trivial that's still
Maybe next nearest neighbor interaction.
Yeah, but I think these ones, they become interacting terms. Yeah, that's right,
No,
because,
but the CFT would still be the.
oh, right, but you would have to, then you'd have an interacting fermion problem, and then you would have to study that. It's not any easier than the original spin model. So for sure, people, we often bosonize or we fermionize spin chains in the hope that, maybe we get some insight, but in general, you get a harder problem. Like for example, like the XXZ spin chain, it's a hopping term plus a nearest neighbor interaction, density interaction. Well, that's not any easier than the original spin chain problems. You can bosonize, then you have liquid physics, right? You can do RG. You're not hopeless, but you don't get an exact solution is the point.
Right.
Maybe some of these are integrable. You can do beta ansatz. Yeah. You can still do beta ansatz, of course. Sure.
So, if you just look at it in terms of in the indirect version of this duality, it's just between critical bipolar theory and then the Majorana CFT, right? So on one side you have like an interacting CFT, and on the other you have a free CFT. But all the critical exponents and stuff that I think calculate, usually the textbook calculations, just do it in the bipolar theory. They don't do it in the Majorana.
Well, this is where the sort of full story from a CFT standpoint, it's everything, right? So it's an Ising CFT, which has, various primary fields. There's a sigma field, there's a fermion, and there's an epsilon field, right? So there's a sigma field, which is, the original spin essentially on the lattice, right? And then you ask, what are the scaling fields? Well, there's a sigma, some primary field that essentially corresponds to this lattice sigma field. There is an energy, there's an epsilon field, which corresponds to the the energy density, the sigma I, Z sigma I plus 1 Z. That's another primary field. And then there's a fermion, which is the Jordan-Wigner fermion. So they're all there, and they have various non-local properties, these various commutation relations that, so all these order fields and disorder fields, they're all there in a sense in the sort of full. Yeah, so then you may project out these things in the lattice model, right? So if you have
data,
yeah.
The fermion is not a local operator.
So the OP has branch cuts.
Primary is epsilon and sigma. Then that's the Brazoro primary is creating CFT and you don't need anything else.
Yeah, I think if you think of it abstractly as a minimal model, right, the 4-3 minimal model, then I believe, all these scaling dimensions. If you define the theory algebraically, right, as in terms of representation theory, then I think these objects are there. But I don't know. This is a bit outside my
local operators.
Yeah, that's right. That's right. In the original, that's right. In the original spin model, it's not a local operator. That's right.
Where are you saying there's a local fermion in the CFT?
Well, you can start. I don't know. Yeah, there's the original sigma, there's the mu, the disorder operator, but then there's their product, which is the fermion. And sure, if you look at all these objects, they're mutually non-local. But my point is that you could start from a free Majorana theory, and then it's a conformal field theory, and the fermion is a primary field, and then the sigmas in terms of these guys are complicated objects.
Let's see if you want to. Maybe I think CFT, do you need to include anything else beyond these two, or?
Well, I don't know.
What if you confuse the sigma and epsilon.
Yeah, I don't know. Sigma cross epsilon is something. I don't know. I'm not an expert in CFT, so yeah, maybe we should stop here and we can discuss these details offline. So,
Thanks.
sure, thanks.